Imagine you're sitting at your desk, you open your browser, type in a web address, and within seconds, a fully loaded page appears. It feels instant. But behind this seemingly simple action is one of the most complex and fascinating systems ever built by humankind. The internet is not just a cloud floating somewhere above us. It's an intricate web of cables, servers, protocols, and devices, all working together to move information across the globe in milliseconds. The journey of your request begins the moment you hit enter. Your device sends out a data packet, a small chunk of digital information, asking for the website you want to visit. But your computer doesn't know exactly where that website physically lives. That's where DNS, domain name system, comes in. DNS is like the internet's phone book. It translates the human-friendly name, like example.com, into a precise IP address, a numerical label that points to the exact server storing the content you want. Once your computer knows the IP address, the request is sent through a series of routers. These are specialized devices that decide the most efficient path for your data to travel. It's like asking for the fastest driving route from your city to a faraway destination. Except here, the roads are millions of kilometers of fiber optic cables running under oceans, across continents, and through cities. Some of these cables are truly monumental. Submarine cables lying at the bottom of the ocean connect continents and carry over 95% of international data traffic. Inside them, pulses of laser light travel at nearly the speed of light, encoding the ones and zeros of your message. In just a fraction of a second, your request can cross from Europe to North America or from Asia to Africa. When your request reaches the target server, say the one hosting your favorite website, the server sends their requested data back the same way, in the form of packets. But here's the trick. Large files are split into many smaller packets, sent separately, and then reassembled by your computer in the correct order. This happens so fast that you perceive it as instant loading. Every packet of data traveling across the internet follows its own path. Some may take a direct route, others may hop between multiple networks. This process is called packet switching, and it's one of the reasons the internet is so resilient. Even if one route is damaged, for example, if a submarine cable is cut, data can be instantly rerouted through alternative paths. The speed of this entire operation depends on several factors: the capacity of the cables and routers, the distance between your device and the server, and the quality of your internet service provider's infrastructure. High-speed connections rely on fiber optics, where information travels as pulses of light. In contrast, older copper cables transmit electrical signals, which are slower and more prone to interference. But speed isn't everything. The internet must also ensure that your data arrives securely. That's where encryption comes in. Most modern websites use HTTPS, a protocol that encrypts the communication between your device and the server. This means that even if someone intercepted the data packets mid-transit, they would see only scrambled, unreadable information. Another layer of the internet's complexity lies in protocols, standardized rules that dictate how devices talk to each other. The two most important ones are TCP, Transmission Control Protocol, and IP, Internet Protocol. TCP ensures that all packets arrive complete and in the correct order, while IP ensures they are sent to the right address. Together, they form the foundation of internet communication. What's truly mind-blowing is the scale of this system. At any given moment, billions of devices, computers, smartphones, servers, IoT gadgets, are sending and receiving data simultaneously. And yet, through the genius of packet switching and global routing, the internet handles it all without collapsing. At the heart of the internet are servers, powerful computers that store websites, videos, applications, and databases. When you visit a website, your device sends a request to a server, which processes it and sends back the necessary files. These servers are housed in data centers, massive climate-controlled buildings designed for maximum uptime and security. Inside a data center, you'll find rows upon rows of server racks blinking with activity. Each server is connected to high-capacity fiber optic lines that link it directly to the internet backbone. Redundant connections ensure that if one link fails, another can instantly take over. To keep this infrastructure running, data centers have backup power systems, huge batteries and diesel generators that can keep operations going even during a citywide blackout. They also have cooling systems to prevent overheating, since thousands of servers running simultaneously produce an enormous amount of heat. Between you and a server stands a whole hierarchy of network infrastructure. After your request leaves your home network, it travels through your ISP's routers to regional internet exchange points, IXPs, then to backbone providers, and finally to the server hosting the content you want. This journey happens in milliseconds. Large tech companies like Google, Amazon, and Microsoft operate global networks of data centers strategically placed so users around the world can access data quickly. These networks rely on content delivery networks, CDNs, which store copies of popular data in multiple locations. This way, if you're in Europe and request a YouTube video, you'll likely get it from a nearby European server, rather than one in the United States. And beyond the visible web, the part we use daily, exists a vast hidden layer known as the deep web, containing private databases, secure networks, and internal systems. Beneath that lies the dark web, a small encrypted portion of the deep web accessible only with special software like Tor. Beyond the wired infrastructure, the internet also thrives thanks to wireless technologies. Mobile networks like 4G, 5G, and eventually 6G are designed to handle massive volumes of data on the move. When you use your smartphone, it connects to the nearest cell tower, which then routes your data into the broader internet infrastructure. Modern cell towers are equipped with multiple antennas and advanced beam-forming technology, which directs signals toward your device rather than broadcasting in all directions. This improves speed, reduces interference, and increases network capacity. Wi-Fi works differently. Instead of relying on cell towers, it connects your device to a local router, usually linked to a broadband connection. In many cases, this broadband link is fiber optic, giving you high-speed access right inside your home or office. In remote areas where laying cables is impractical, satellite internet becomes essential. Older satellite internet systems suffered from high latency because data had to travel to geostationary satellites 786 kilometers above Earth. But new constellations like Starlink operate in low Earth orbit, LEO, at just a few hundred kilometers up. This drastically reduces delay and allows for speeds comparable to traditional broadband. No matter the method, fiber, wireless, or satellite, all these systems work together seamlessly. You might start a video call at home on Wi-Fi, walk outside and continue on 5G, and still stay connected without interruption. This is possible thanks to sophisticated handover protocols, which instantly switch your connection type while keeping data streams intact. What's perhaps most mind-blowing is that all of this, billions of devices, zettabytes of data, thousands of networks, functions without a single central controller. The internet is decentralized by design, governed by open standards and maintained by countless organizations worldwide.